Okay, time for some pre-calc. What I meant to say was, hey everyone, it's Mr. Canfield. Okay, time for some pre-calc. Oh, dreaded slurp, I'm so sorry. Okay, today we're talking about inverse trig functions. I debated skipping this. It's important enough to spend time on. And you can even see, while inverse trig functions should have been covered in a trig or pre-calc course, they are covered here in their entirety because their definitions are instrumental in taking derivatives of these functions and subsequently taking integrals that yield inverse trig functions. Okay, so here's the deal. These integrals, basically, you memorize them, you memorize the derivatives. They might be an AP question. Like, every year there's just one of the 6. And you just have to know all 12 of them because they're derivatives and integrals, and they're super annoying. But they're also super formatty. Like, you'll notice, oh, there's the format of that, and oh, there it is. Okay, it's that one. So I'm not just going to jump to the formulas. I'm trying really hard. I really want to, but we're not gonna. All right. So this is also a really good opportunity for us to talk about unit circle business. So I'm probably going to do that as well. So the first thing that we need to wrap our heads around is that inverse sine, inverse cosine, inverse tangent have restricted y values, restricted possibilities. So let's remember what these actually mean. So inverse sine, that was a way for us to say, okay, so normal sine, right? Normal sine was you plug in an angle, you get out a ratio, right? So like sine of pi over 2 is equal to 1. You plug in an angle, you get out a ratio. Inverse sine, you plug in a ratio, you get out an angle. So this was theta in, ratio out. Inverse sine is ratio in, theta out. That's true for all of these. And remember that they can say sine inverse or arc sine. Here's the problem with arc sine, though. If I say, hey, when do I get a ratio of 1? It happens at pi over 2. The thing is, since it's a circle and it's cyclical, it happens at pi over 2, add 2 pi to that, right? 5 pi over 2, add 2 pi to that. 9 pi over 2, add 2 pi to that. 13 pi over 2. It happens an infinite number of times. And so to keep these functions as just spitting out single values, we say inverse sine. Here, I'm going to draw a half circle. Inverse sine goes from pi over 2 all the way down here. And we, instead of saying 3 pi over 2, we say negative pi over 2. So inverse sine belongs somewhere on this half, as well as inverse tangent and inverse sine's buddy. And one of the reasons that we do this is now there's only one possible answer. If I say, hey, what's the inverse sine of 1? Everyone knows it's pi over 2. Well, not everyone knows. Like, across the math world, there's only one. We're all going to say it's the same thing. It keeps us consistent with each other. The other 3 go from 0 to pi. It's the top half of the circle. Notice how neither one involves that bottom left, the third quadrant. So we have cosine, cotangent, and cosine's buddy. I didn't really know this until I taught trig, but you guys are further ahead than I was at your age, so. Okay. So there's those things. So I'm going to do a unit circle approach to a couple of these, and then I'm going to start using my non-unit circle approach. Because if you still don't have the unit circle down, that tells me that you're probably not going to spend the time to get it down. So let's see. Okay, arcsine of -1/2. Well, let's see. Arcsine of -1/2. I know that on my unit circle, a y coordinate of -1/2 would be down here. And I just need to think, okay, well, that's going to be -1/2. That means this is going to be √3/2. That is going to be, what, pi/6, but down here, like 11 pi/6. But since it's down here, we just say it's -pi/6 instead of saying 11 pi/6. That's my unit circle approach. That works with all these. If you got your unit circle, these are easy. Let's say we forget all that. You need two things to be able to do basically any trig. Any trig that we're going to do. All right. The things that you have to know that 30 degrees is pi/6. You have to know. Now, and this is so easy, right? 3 and 6 are switching. 3 and 6 are switching. 60 degrees is pi/3. And then the 45s are split. They're in half. It's √2/2. Whoa, Canfield. God, you did not just say that. 45s, it has a 4, pi/4. Got ahead of myself, okay. And this is a 1, 2 square root of 3 triangle. This is a 1, 1 square root of 2 triangle. And I'm just telling you the way that this is legit the way that I did trig. I never learned the unit circle. I had these things memorized, and you just build it every time. So in the 30, 60, 90 triangle, we know that, well, in every triangle, the smallest number always goes across from the smallest angle. So 1 goes here. Now, don't be fooled. I always feel like 2 is smaller than √3 because 3 looks bigger than 2. But remember that square root of 3 is 1 point, I don't remember. But this is actually 1 point something. So this is our middle child. This is the middle number here. So 60 is the middle angle. So this is √3. And the biggest angle is our 90. So that's 2. On the 45, 45, 90, it's 1, 1, and √2. 1 and 1 and √2. Okay. With these two triangles, arcsine of -1/2. I'm trying to find a triangle where I get -1/2. Well, 1/2, the only place I could see that is 1/2. Oh, and the sign would be 30. So I use 30 to get 1/2. But I'm trying to get -1/2. So that tells me that I'm going to have to go. I remember we can only be in this half for arcsine. So if I want to get a y coordinate of -1/2, I got to go down here. That's 1 and that's 2 like that. Oh, so then that means that this is my 30-degree angle. Oop, -30 degrees, or -pi/6. I definitely think in degrees when I do it this way, and then I convert it. So B, I'm going to just be building these. I'm going to build all my answers. So B says inverse cosine of 0. So remember cosine, oh, there's no triangle that has this ratio of 0. So I'm looking for instead either an x or a y coordinate. Well, cosine's x coordinate. When do I get an x coordinate of 0? I get that here, right? At 90 degrees. 90 or pi over 2. Okay. The power of this triangle method shines on our next question. Our next question says inverse tangent of root 3. So if I go to my two triangles, only one of them actually has a root 3, so I know it's got to be either 30 or 60 or 90. Then okay, so 30, no, it can't be 30, right? Because tangent's SOHCAHTOA, right? Opposite over adjacent, 1 over root 3. No. I want root 3 over 1, so that tells me I want 60. Tangent of 60 gives me root 3 over 1. Oh yeah, that's pi over 3. The power of this shines again here. Cosecant inverse of negative root 2. Okay. Cosecant goes along with sine, right? It's 1 over sine. So I want to know what angle gives me an upside down sine of root 2. Well, I go to my first triangle, and I'm like, wait, that's got a root 3, not a root 2. This one has a root 2. And it says it's negative. So that says it's got to be like down here. Sine, 1 over sine is root 2. So instead of being opposite over hypotenuse, we'll reverse it and do hypotenuse over opposite. So hypotenuse over opposite gets me root 2. So that's this triangle, right? And it's going to be root 2 over 1. Oh, yeah. Oh, it's a 45-degree angle. Okay. Oh, but it's down here, right? So to make it down here, we say negative 45 degrees or negative pi over 4. And these are all doable if you have the unit circle nailed. Okay. Next part. Evaluate the following. Okay, these are some of my favorite problems to do in pre-calc. I don't know, they're just fun little puzzles. So it says sine arctan 3/4. Okay. All right, so it's saying take the sine of whatever angle we get with tangent of 3/4. And all you have to do for these is ignore the outside. Just focus on the inside first. Arctangent of 3/4. That means there's some triangle. Oh, and tangents in this half, right? So I know it looks like this. It doesn't look like this because it's not negative, right? So arctangent is 3/4. Okay. So I'm going to call my central angle here theta 3/4. Tangent is opposite over adjacent. So opposite over adjacent, opposite over adjacent. And it's this angle here, theta. We don't know what theta is, but we do know that all we want to do is take sine of that angle. Okay, well, sine of this angle, using SOHCAHTOA, is opposite over oh, I don't know my hypotenuse. It's all over. I quit. No, just kidding. This is a special right triangle. We know the hypotenuse if you know your special right triangles. If you don't remember it, well, hey, use the Pythagorean theorem. So 3 squared is 9, 4 squared is 16, c squared is, oh, I still don't know. 9 plus 16 is 25. So c is 5. So what's opposite over hypotenuse? There are some mad lads out there that will do this without doing any work. Good for you. I am not one of those mad lads, especially in my videos where I'm trying to make sense out of things. So let's think about this one. Arc cosine of root 2 over 2. And I'm going to be taking the tangent of said angle. The cool thing is I don't have to know this. I just have to go, okay, let me draw my triangle. Call this theta. Root 2 over 2, cosine is adjacent over opposite. Adjacent over hypotenuse. So there's my adjacent, there's my hypotenuse. Okay. I feel like I did this wrong. My brain's like, what's going on? Oh, silly me. Okay, sorry. I'm back. I was locking up because I was like, I feel like this isn't going right. I should just trust the process, right? We did arc cosine root 2 over 2. This feels wrong, but I don't know my third side, but that's one of my legs. So I can say root 2 squared plus my leg squared is equal to 2 squared. Root 2 squared is 2, plus b squared is equal to 4. B squared is equal to 2. So then b is equal to the square root of 2. And so tangent of theta is equal to 1. And sure enough, if we use our unit circle, this one's way easier, right? Arc cosine of root 2 over 2. Oh, we get cosine root 2 over 2 at pi over 4, right? What's tangent of pi over 4? Well, it's root 2 over 2 comes root 2 over 2. So it's 1 when we take the tangent. So this is one where, like, you can do this in your head if you know your unit circle. Or if you forget everything, you can still do it. Okay, not everything. C, secant of inverse sine of 1/3. Okay, inverse sine of 1/3. Draw our triangle. Opposite over hypotenuse. I'll need to find my third side, right? Because this is my angle. So I'm looking for secant of this angle. So 1 squared plus, I'll call this one a, is equal to 3 squared. So that's a squared is equal to 8, right? Because that's 1 and that's 9. 9 minus 1 is 8. So this is the square root of 8. Remember, that's 4 times 2, so I can rewrite this as 2 root 2. So secant, remember, is the reciprocal of cosine, and cosine would say this over that. 2 root 2 over 3, excuse me. So secant of this would be 3 over 2 root 2. And D, cotangent of inverse cosine of -2/5. All right, our first one that we actually have to use our knowledge of what's allowed. So this says inverse cosine is -2/5. This triangle does not make sense because it's adjacent over hypotenuse. Like, spatially, we don't say this is -2, so it has to go this way. And this is where we never go in the third quadrant. That's really one of the main ideas with with inverse trig is we avoid the third quadrant, because if, technically speaking, we could also go down here and there would be another possibility. But if we say with inverse trig, if we avoid the third quadrant, we'll always be fine. That's kind of the shortcut that I'm only realizing now after teaching pre-calc for over 5 years and teaching BC for 2 other years and teaching AB for 5. Way too long to have just realized that shortcut. As long as you avoid the third quadrant, inverse trig's easy. Okay. So we get cotangent of our angle. So cotangent is, instead of opposite over adjacent, it's adjacent over opposite. So let's see, that's 2 squared plus b squared is equal to 25, right? 5 squared. So that's b is equal to the square root of 21. So adjacent over opposite, we get negative 2 over root 21. And just remember, for stuff like this, a lot of times people will rationalize. You could see negative 2 over root 21. You could see negative 2 root 21 over 21. Either one of those, they're correct, and either one of those is plausible for us to see as an answer choice. So